what? 14.000 kilobit sekund. 14.000 qo'ygan, 14.500 qo'ygandim men.
Kanal gitar çıkmayapti.
Nima chiqmaydi dedi. Okay, stream output 14.000 kilobit per second. Okay. Video bitrate is 14,000 kilobit per second. 14,000 kilobit.
Arka boku baksın. Benim şöyle çıkarak sen mi?
90. işte Forka biz. Men hozir Forkada ekanman aka.
Ya çıkarak.
Hozir bizda Forkada ekanman men. Anyway, it doesn't matter. Okay, welcome guys, welcome guys. It is Friday and today it is holiday in Korea, so it's good. We can do more stream today. We can be more productive today. So let's continue this building a computer from scratch. So we have here. So in our previous stream we did build this for 5 objects, 5 components: NAND, INF, add, OR, XOR. So now we need to build more and more these operations, these logical operations. Then we can kind of compile our computer. How's the voice? Is there a noise? Refrigerator noise, no? Oh, okay, it's high quality. Half adder. And add component that adds 2 bits. Write in chat. The add component that adds 2 bits and output is a 2-bit value. H output is a high bit and I is a low bit. Oh. Okay, we have 2 inputs, A and B, and we have 2 outputs, H and I. When we have 0, 0, we need 0, 0, okay? When we have a 1, 1, we need 1, 0. Oh, interesting. When we have 1, 1, it's only 1 and 0. 1, 0, 0, 1. 0, 1, 0, 1. 0, 0, 0, 0. Interesting. What we can use? If you use AND, let's try AND. 0, 0, if 0 and 0, 0. 0 and 1, 1. Can I just map directly? A to H, B to I. Two bits, add 2 bits. The output is 2-bit value. The H output is a high bit and I is a low bit. Because 1 is 1, right? And 1 is just 1. 1 bit is 10 bits. Kind of. 1 0 bits. 2-bit value. Let's design this one. inf and it is alarm. Okay, 1001. Can I use like this? Okay, it means it's working, but it's working for only one case. Look, when we want to do this one and we achieved it. Okay, and I want to do this one. If I turn this on, okay, in this way. If you have both of them, fine. If you have only one, fine. No, not fine. If you have only one, it should be here. Which condition can we use? Which condition? What was this nan? I forgot. How was this one? What was this here? Okay, anyway, inf. Oh, brother, we have one viewer.
Not me.
Maybe you. Okay, 0 0. When we have 0 0, we need to have a 0. Okay, I think this is easy to do. But the thing is that we need to design this one. We need to satisfy this one and this one in parallel. Do we need XOR or do we need to have OR? Which one? We wrote somewhere, right? Maybe it is in README. Look. When we have 0 0, we have a 0, right? Same like as this one. When we have 0 1, it is 1. When we have 1 0, it is 1. This is good. Except this one. When we have 1 1, it should be 10. 1 0. Here 0. We can fix this one. So I think let's use XOR. So in XOR, when I have 0 0, it will return 0, right? I can connect it to the here and output. This one, okay, this one is 0 or 1. When it changes, you know, when it changes, when we have both of them 1 1. In that case, it's simple, you know, I can connect here and I can just directly connect here. So I think we have our half adder. Let's check it. Okay, next level. Congratulations, we did it. Next operation. Full adder. An add component which adds 3 bits A, B, and C. The output is 2-bit value, and H output is the high bit, and I is the low bit. Oh, okay. Here we have 3 inputs. 3 inputs, okay. And then we have 2 outputs. Let's understand it. If you understand this electric circuit, these operations, so we can just program easily, you know, like freely, and enjoy the programming because we can understand better. Okay, this is a browser. We call it Vim, not Vim, the Qt browser. It is open source browser. I like to use these days. Let me to wear a glass. It is 6 a.m., 6:51 a.m. in Korea. Friday morning. ABC, okay. When we have 0 0, it should be 0. It's fine. When we have 0 0 1, it should be 1. When we have 0 1 0, it should be 1. When we add 0 1 1, it should be 1 0. When we have 1 0 0, it should be 1. When we have 1 0 1, it should be 1 0. We can use similar approach as before. Look, when we have 1 1, it will be 0, right? But I need XOR. Is it what we want? Is this a thing which we want to achieve? Look, when we have like, let's say when we want to add only one thing, we're passing it, right? If we want to add 2 things, it should be 10. Yes. When we want to add 3 things, it should be 1. Yes. Look, passing, this is failing. Why? When we want to add 2 of them, it is showing 0. What if we just add inverse here? Oh, no. Okay, it should be 0. I mean, when we have 1 1, it should be 0, right? Okay, it is 0. It is fine. But this is not 1. It is 0. Okay, this one. If we have this one, and if we have this guy and this guy, no, if we have this guy, We have this guy and this guy. In that case, now if we have anything of 2 is connected, then we can just make it 1. This is 1. This is 1 when two of any elements are both of them 1 1. In that case we can just do add and put it here 1. 0 1 1, right? 0 1 1. We cannot have 3 outputs, right? No, I don't like this approach. It seems very, very difficult one, very stupid one. XOR. If this is 1 and this is 1, this is 0. Oh, what happened? Can we go back? No, we cannot go back. Why? Okay, we have XOR, right? And then I said, what about if we use add? Because we built add. Okay, good. But now we have 3 outputs, right? Okay, our 4 cases is working, but another 4 is not working because we need to work with A also. This one should be 1 when we connect A also. What would if we use another end? Add. What happened now? And let's stick with this one. We have add, right? Fine. When I add 1, this should be turned as 1. I can use OR and say A and I and put it here. No? Really? Okay, let's understand one more time. Let's understand. So when we have all of them, it should be 1, 1. It's fine. Wait, in this case, it's not fine. In this case, it is not fine. In this case, it is 1, 1. Ooh, it should be 1, 0. What about if we connect, add this guy and this guy? Connect, please. With one more add, maybe. Interesting. We have add, 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 add. And then I think we can just delete one of them. 2 is enough. We have AND or XOR, right? So in this case, it should be 1, 1, right? One was is only when this is 1, 1, when H is 1, H is 1, I is 0, I is 0. In that case, it should be 1, 1. In this case, it should be 1, 0. Yes. How about NAND? How about NAND? Look, look, look. Oh, 0, 1, 1, 0, 0, 1, 1, 0, 1. NAND is, I think, using NAND, I think is not good now here. What we can use here is maybe XOR. If we have x0, h0, h0, in that case it should be 1 here, right? Which one returns when we have 0, 0, 1? No? Okay, fine. What about if we use one more add? Stupid. No, no, no. This is not a good idea. But we are close. We are close. We are close. We close. We are close. Okay, we have and add. Can we use add one more time? No, unfortunately. XOR. If we have like this, like 1 0 1 0, it means we have two, right? It means we have two of them. It means we have three items. No, 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 no. We are going wrong direction. We are going in wrong direction. It should not be like that. It should not be like that. Okay, we have two adds. Okay. Actually, what is the add component? Add component is the and XOR. Okay. And an XOR, right? Just let's start one more time from 0. If we have 1 1, it should be 1 0. It should be 2. Okay, we have 1 1 and we have XOR, right? It gives us 0. But in this case, when we have 1 1 1, it should be 1 1. Okay, it should be 1 and 1. do like this. Okay, this is add operation. Was it? Am I correct? Ah, no, no, no. And XOR are like two separate ones. See, see. And XOR are two separate guys. Then we need one more XOR, I think. Okay, we are more closer. We are more closer. See. When it fails, when we have two values, right? Because you know, like, because this space is working fine. Look, when we turn off or on, it should be 1 1. Okay. Oh, no, no, no. It's not working fine. Look, look, look. We have a failure when this b value is 0. It should be 1 0. It is 0 0. This is correct. If it is vice versa, both of them is 1 1. Ah. No. Oh, guys. Let's think. Let's think more. Let's think more, more, more. We need one small component, you know, like here. What it can be? I think it should be some kind of XOR. One more XOR. Hmm. Let's fix this guy. This is complicated. We can do a lot of things here, but here I think we can do like small things. We can like quickly fix this guy. Okay, when we have 1 here, it should be also 1. Yes, fine. If it is off, off. Ah, look. And it's considering only this guy and this guy, right? We need one more and we need to connect this guy and this guy and select or select this guy, select this guy and pass this guy. Now fine. Now we have this switch. Let's switch. Fine. But we are like we left only one condition. It is when we have 1 and 0 and 1, it should be 1 0. Oh, this is working fine. But this should be okay. Our problem is here. This is excellent. This is brilliant idea. But here we have a problem. We need one more end. I think maybe I know it might be stupid idea. Nah, 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 nah. Let's understand the problem quick one more time. Look, the problem is that when we have a 0 here, they are both returning 0, 0, right? When I turn off this B goes this way and this way, and it stops both of them. That's bad. It should stop only one of them. So we need to get AND, okay? And get the A and C. And use OR. Or this guy, or this guy. And pass it to here. Okay, now we have something. I think it is complicated, right? This graph is complicated. And we need to optimize, I think. Here, I think no optimization, but here maybe optimization. But we satisfy all these conditions. That's good. Next level. Oh, but it is possible to solve with fewer components. Of course, we can solve with fewer components. We can just use add, but where to use add? We can replace this one and this one with add. Anyway, for them it's passing, right? We need a passing thing. Passing good. Now build an adder that adds 2-bit numbers and 1-bit carry. Oh my god, what is this? I see, this is how computer works, build an adder that adds 2-bit numbers and 1-bit carry. Input A1, A0 is 2-bit, B1, B0, 2 bits. Input carry is 1 bit. Look, we have 2 of them here, we have 2 of them here. 2 plus 2, it would be 4. 4 plus 1, 5. And 5 represented is 1, 0, 1. I have add. I cannot connect like directly because this is 1, this is 0. It means there is two values. I mean the size is 0. It's not only 1 bit, it's 2 bits. So I need to represent it as 2 bits. 3 bits. If it is like this, it should be 3 plus 3 plus 1. 6, 6, 7. It should be 7 here. I will put 7. 6, 7. How many levels left? Okay, multi-bit adder, increment, subtract, equal to 0, less than 0, select, switch, logical unit, CRT, data, flip-flop, register, counter, RAM, combined memory, control. Oh my god. We need to do a lot of work. We need to do the work. Let's continue, let's continue, let's continue. Okay. Okay, guys. Maybe we're missing something. Imagine that you are now in 1950s, okay, no, 1940s, in Second World War, and it is like 1941, let's say, and it is August. So when actually the Second World War started, like officially, I think it's 2020, 1941 in spring, I think. Oh, first September. No, no, no. I mean in 1991. 1941. Actually, it doesn't matter, you know. It's okay. It started in 1st September, okay? Okay, it started in 1st September in 1939. Yeah, because in 1941, 41, uh, the Nazi Germany starts to attack to the USSR. So in that at that time, then it was like, you know, like officially become like world war, because at that time the USSR started joining the war. So let's say 1939, and if it is 1st September, then 15 days before. No, no, no. Okay, assume that you are in 1943. Okay, 43, in the middle of the fight, when you are not sure who will win, when you see that the German Nazis are almost capturing the Moscow, so, and you see that maybe like in between US and Japan also there is a rivalry. So in that case, you need to discover these things. You need to open by yourself. You need, if you open, if you and you are sitting in maybe in US or in somewhere that, and you are thinking about this, how you can build a software which can help to win a war, okay? Just fix your mindset. Let's continue. Let's continue. If you fix this problem, then you will win. You will be hero. You will win the war. You know, like the the biggest, the terrifying war in history. This is on the same level as creating atom bomb. Okay. So if we have 3 inputs, so we can use this add easily. You know, we build add to solve this one, and these levels are built in the way that it is incremental always. So here, if you have C, it is 1 value, right? Let's connect C to C. Assume if it is all a 0, in that case it is just 1. 1 should go here. Okay. If this is 1 1, it means we have here 1 2 3 3 values. Okay, here we have 3. This is 2. This is 3. This is 1. Oh, we can do like this, right? Look, when we have 0 0, it is 0 0. When we have 1 1. When we have 1 1. When we have 1 1 1. Oh, excellent, 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 good. Okay, good news, good news. We are doing progress. Actually, we did nothing right here. Actually, it's nothing, right? Nothing special. There's nothing special. It should be 10, right? One one one. It should be 1 1 1. It should be 11. Yes. It doesn't make sense. Why? Why it doesn't make sense? And right. Now we have just 1 1. Like stop this one. Look. Here we have 3 values, right? And we are just getting another 3. We are losing this guy. You cannot add it here. This is not 1 value. This is 3 values here. It is wrong to do that. Then what to do? Then how? What do you suggest? In like how I did the add, right? I used XOR and I used AND, right? Okay. So we need a a special gate here, special operation here, which will obtain these guys, which will get from these two guys and put it here. We are not depend on C, C can be 0, C can be 1, etc. Okay, what we can do? Think more. Thinking. Tafakkur, we call it tafakkur. Bas. Yeter bas. 0 0 0 1 1 1 0 0 0. Okay, if we add. How we can convert this information to this information? Let's omit this guy. I don't like it. I don't like this. Let's build a table, okay? Look. We have only one value, right? 2, 3, 4, 5, 6, 7. Am I correct? Didn't I make any mistakes? 1 1 0 1 1 1 0 0 1 0 1 1 1 1 1. I think it should be correct, right, guys? So here, if it is 5, then it should be 1 0 1 1 0 1, should be 1 0 1, because here 1 1 it is what? 1 1 is 3. 3 plus 3 is 6. So it should be 6. 6 is what? 1 0 1 1 0. So if you have this thing, it should be 1 1 0. What about in this case? Okay, let's make a condition. These problems are not that difficult, If we have 1 1, what? 1 1 and 1 1, output should be 1 0, right? 1 1 0. What is the output? 1 1 3 4 2, 2, 3, 5. Do you see anything strange or any? Can you catch any kind of any pattern, any design, any? How can I say? Can you observe a pattern or similarity or like uh, some kind of? Can you put it to the formula that we can implement it here? Look, can I use and? So if it's 1 and 1, it is 0. 1 and 1, 0. 0 and 1. 11 and 0, 1. It's 100. 0, 1 and 0, 1. 1, 0. 10 and 10. 0, 1 and 10. 0, 1 and 10 is 11. 10 and 10. 10 and 10. 10 is 2, 2, 2, 2. 100. When both of them are 1, it is 0. See, and then 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. No, if it is 1, 1, it should be 0. XOR. We are passing this condition, but we are not passing the second condition. So still I don't know. I need to discover. Still I don't know how to do it. Look. When we have everything 0, 0, 0, 0, 0 except s is 1, it should be 1. Right? Simple. Simple, right? So if everything is 0, 0, 0, 0, it means 0, right? No, it's not good. It's not good. It's not good idea. And then what? Because this value represents 2 bit. It doesn't represent 1 bit. But this represents a bit, 1 bit. This is 2 bit value. This conversion doesn't help. Because this is also still 2-bit. You see? This is a problem. Because they are in different dimension. I mean, this is 2-bit, this is 2-bit, this is 1-bit. So we need to think carefully. We should think. We should think. So this is 2-bit, 2-bit, 1-bit. Then the question is that where we should convert. Should we stay in 2 bits or should we stay in 1 bit? Should I convert like should I convert this 2-bit value to 1 bit or should I convert this 1 bit to the 2-bit? Which is easy? Which one is easy? Which one is easy, guys? Which one? I think 2-bit, staying in 2-bit. So if it is C equal to 0, but output is in 1 bit. No, we need to convert to binary, you know, like we need to convert to 1 bit. Otherwise, it is too difficult. I mean, not too difficult. Otherwise, I don't see, you know, like I don't see any easier plan. Because if we use it in 1 bit, we can use this NAND, INT, add, or XOR. I'm sure there should be a trick. I'm sure there should be a trick, much more clear, much more clever way. But what can it be? I don't know. Now we should check my voice, you know, because I turned on power of my PC or my laptop, and I have microphone. They have some kind of, you know, like problem between each other. So let me to listen to our stream. Stream. So I need to go to YouTube this moment, and here I think there is no noise, right? Is there a noise? Small? No? That's good. That's good. That's good, guys. We are in good shape, in the right way. Okay, let's go. Because the input is 2 bits, you know, like 2-bit way, 2-bit number, 2-bit number, 2-bit number, 1-bit number, 2-bit number, 2-bit number, 1-bit number. Convert 2-bit to 1 bit. This is not converted to 1 bit. This is not converted to 1 bit. Delete it. It's not working. So let's just think about this one and this one. When it is 1 1, it should be 1 1 1, right? We can use XOR and AND. But here we cannot use XOR, we can use OR. I'm, it's better to use OR, I think, here. If we use 1 from here one more time, in that case it will be 1 bit. Yes, that's right. We don't need this, guys. I understand, I understand. I understood the problem. I understood the problem. I understood the problem. Look, when we have 1 1 1 1 1 1 1 1, it should be 1 1 0. When we have 0 1 1 1 0 1 1 1, it should be 1 0 0. Okay. What does 1 1 1 7, right? No, when we have, look, when we have 1 1 1 1 1 1 1 1, it should be 1 1 0. 1 1 0. Look, when we have 1 1 1 1, it should be 1 1 0. 1 1 0. I need a help. I need a help. I need a help. How to fix this? How to fix this? This is converter. Converts 1 bit to 2 bit, right? And vice versa. We should fix our posture. This depends on XOR. Yes. Yes, let's go, let's go. You know, we can use add. Add this one. Add this guy. And add this guy. Use this one, use this one. Close. Check solution. Yes. Yes. We are in right direction. We need water. It is 7:55 a.m. We need to think about this guy and these guys. These two guys. Because these two guys are smart. Let's see the pattern. What kind of pattern can we get? When it is 1 1, it should be 11. When it's 0 1, it should be 1. It is 1 1, it should be 10. What? Look, when it is 1 1, it is 1. When it is 0 1, it is also 1. When it is 0 0, it is 0. Look. 0 0, output should be 0. 1 1, output should be 1. 0 1 should be 1. What is the pattern? It is OR. Can you just directly connect? Let's just connect, let's see. No. These guys should talk with these guys and then decide where to put it. So let's tackle this problem. Okay, we have 0, 0, 1, 0, 0. It should be 1, 0, 0. Why? Actually, why it should be 1, 0, 0? Because this is two values, right? Output should be 2, no? 10, what is 10? Doesn't make sense. Output should be 1, 1, 0, 1, 0. Yeah. Output should be like this, okay, yeah. Output should be like that. And when we have this one or this one, output should be like this one. It solves a lot of problems, you know. Definitely, it will solve a lot of problems. See, except because we are not talking with this guy. Why we're not talking with this guy? We can talk with that guy, but you know, when we talk with this guy, we only talk with this guy when this is one and this is one, right? And can I say like that? Can I say? Let's check it. 0, 0, 1, 1, 1. Output should be 0, 0, 0, 1, 0, 0, 0. Okay. Let's make it like smaller. I cannot catch it. I cannot see clearly. Okay, we have a lot of space now. We can see clearly, right? You can see it, right? Okay. 0 viewers, doesn't matter. Okay. Look, when it is 1 and 1, it should be just 1, 0, right? Should I replace OR with XOR? Why? In that case, it will be 1, 0. Let's check the first case. Let's check this one, okay? Just B1 is 0, B1 is 1, and 0, 0. In this case, it should be 1, 0. Okay, makes sense. Makes sense. Makes sense. When we have 1, 0, 1, it should be 100. It should be 100. 1, 0, 0. But we are getting 1, 0, 1, 1, 1, 0. Why? Should I replace this OR with XOR? good end. No, no, wait. 10 plus 10, it should be, 10 plus 10 should be 100, right? No, 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 no. It is incorrect. It is incorrect. It's incorrect. Look, if we have a 10, okay, let's say if you have 11 plus 11, it should be 110. Let's just think about 10 plus 10 again. 10 plus 10 is 100. If it is 1 and 1, it should be 1. If it is 0, 0, it should be 0. I mean, this one is probably should not decide this one. What if we replace the place? Okay, we are missing some conditions, you know. We are missing some conditions. And or and when we have 10, 10 it should be 100. Hook this out, okay. 1 0 0. If it's plus 10 plus 10, 10 plus 10, it should be 1 0 0. 1 0 1. Okay, it should be not end. When we had plus 10, it should be 1 0. Okay. No, no, no. When we have 0 and 1, we need 0. And again. No, 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 no. See, when we have a 10, it should be. This OR is not working. Oh my god, it's difficult. So here we have 0 0 1 0. It should be OR XOR and. No, it should not be like that. This is incorrect. Look, this is 1 bit, okay, but this is 2 bits, high values. If it is 0 0 1 0, it should be 1 0 1 0. Okay, 0 1 0 0 1 0 0 1 0. We said if we use OR, we can get it right. We said it is 1. We said it is 1, right? It will be 1. If it is 1, 1, it will be also 1. 0, it will be 0. If we did like that, it passed, right? If I connect like this, it's passing more. And we said we should add AND. No? Look, 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 look. Because this is incorrect. We can't directly add it. We cannot directly add. We cannot directly add it. Then what? Then what? Then what? This is high dimension. This guy, and this guy are high dimension. Okay, we should use them wisely. How? How? Okay, if you have a big problem, if you have a difficult problem, if you have a complex problem, we need to divide it, or we need to solve a simpler problem. We did solve a simpler problem. We did solve this add. We used XOR. We used AND. We used OR. And we have this add component. But this add component doesn't work because that inputs 1 bit, but we need the 2 bit. Two bit. If exists problems, we can think we should talk about like RISC-V, RISC-V, other architectures. They are very interesting. Very, very interesting. It's really powerful. So here we have OR, we have AND, right? And we have this one. This is high dimension, right? 1, 1, 1. Stop. 1, 1, 1. 1, 0. 1, 1. Oh, really? We did it, guys. How simple. Okay, I definitely did overthinking, so we couldn't solve it. But now we did it just because simply brute force. 16 bits of output as a unit. Display the output as hexadecimal and a signaled decimal. You are now ready to start working on 16-bit numbers. Oh, now we are ready to go to next level. Okay. Your mission is to build an increment component that add 1 to the 16-bit number. Because you are now working with 16-bit numbers, we have simplified the representative of the diagram. Instead of 16 separate wires and connectors, they are bond bundled together and shown as a signal as a single connector, indicated by a small 16 label. Insert mode. Yes, insert mode. In Vim we have insert mode, visual mode, caret mode, insert mode. So kind of mode. Everywhere is mode. Actually, I don't understand the problem. Let's see. Add 1 to 16-bit number. What is 0? Constant 0, okay. If it's input 0, output should be 0. Yes. Decimal means our human readable, human numbers. Expected one. Can I use this one? No, it doesn't help. What happened? They are very easy. Now they are really very easy. Piece of cake. Piece of cake. Piece of cake. It is 8:23. 8:23. We need to exercise, guys. We need to exercise. We need to exercise. Oh, this is the simplest possible solution. I see. Congratulations. What to say? I don't know. Let's go. Let's go. Let's go. Now build a component to subtract. Okay, now we need to subtract. We have a description here. Okay. Output A minus B as 16-bit number. If result is less than number is 0, it is represented as plus result. Example 1 0 minus 1. Now you see, right? Now you understand, right? First we built, we built this NAND, invert, and or XOR logical gates, and then we are moving to these arithmetical gates, and then we built switching. All is based on power, A and B signal, just passing through the power, A signal, B signal. What is the A signal and B signal? If you have a power, it means 1, right? Like we can go with this one. Let's see. And we have the key open or closed, and we have a relay. Just simply see how beautiful, how amazing is this. Subtract. So now if we build arithmetics, switching, arithmetic logical unit. So there's arithmetic logical unit is inside of every. I'm not sure, but I think it should be on every chip. On every chip. On every chip. Doesn't matter. Maybe it is a RAM memory, it is a RAM chip, it is processing chip, logical chip, etc., etc., etc. Oh, wow! This is amazing. Amazing, 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 amazing. So now we need to subtract. Subtract two values. What does subtract mean? Subtract means from one thing we should reduce certain amount. We have something, we should reduce some amount. And we should represent this last one. A minus B, right? Then we should return just A. Correct. And then another thing which I learned today with you is that look 1 0 1 is identical to 0 0 0 1, identical to 0 0 0 1, identical to 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. 1 0 equal to 0 1 0 equal to 0 0 1 0 equal to 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. You see what I mean? 16-bit. Last one is 16-bit. That's how computer works. That's how simple. Actually, I am hungry. I'm hungry. I need to exercise, you know. It's difficult to sit in one place and, you know, just do this boring stuff. They are not that boring. They are interesting, but sitting is boring, you know. I should not sit. Sitting doesn't, you know, it makes me lazy. It makes me to not think. Let's stand up and think. I haven't implemented my subtraction before. It's first time. It's first time when we are implementing this minus. I think I should turn off my background, right? If I turn off my background, then oh, it turned on. Oh, really? What? There is a bug. I like this one. No, I don't like background. Can I just choose no? Oh, I like this. But guess where? What place is this? Okay, this is now the weather looks like. Actually, it's a more cloudy. Doesn't matter. Doesn't matter. Doesn't matter. We need to implement subtraction. Subtraction. We need to implement subtraction. Let's just type it, you know. Let's just type it. We are wasting time. Let's just type it. Zero one minus, let's see, 10 minus 0. 10. 0 1 minus 0 1. 0 1. 1 1 minus 0 1. 0. 1 1 minus 10 equal 0 1. See? So it means we are going back. If it is 0 and 0, if it's 0 and 1, it's 1. 1 and 1, 0. 1 and 0, 1. 0 0 0. This is also XOR. XOR, where is XOR? A plus B. This is plus, right? But I want to make it minus. So we need to plus negative value. Oh, you can't see me, right? Okay, now you can see me. We need to implement minus. In that case, this B value should be smaller. Now it's very big. Way much bigger. No, guys, my brain isn't working. My brain isn't working. Oh, we have a drop rate. We have a dropped frames, 0.3%. Oh, it's almost 2 hours. In 2 hours, we just solved how many problems? 4 problems. Not bad, but slow, guys. Slow, slow. Okay. Let's just do small steps. If it is 1 minus, if it is 0, 0, 0, 0, what is end? No, it's stupid. We don't have end. Why we don't have end? We have NAND. Inversion, increment. Okay, we have passing. Why are you doing like this? When we have 0, it should be 0, right? Yes. When it is 1, it should be 1. When it is 1 minus 1, it should be... When 1 minus 1, it should be 0. Okay, we have one viewer. Welcome, welcome. So here, we have a NAND component. We have invert component. We have 0. We have OR. We have increment. We have add. Can we use add here? Yes. A is A. B is B. C is C. Check solution. Yes. +1 incrementation. One. Gapirib stream qiling. Okay. Oops. Okay. I'm stuck. You should help. I cannot solve this problem. I need to implement a subtraction between 16-bit numbers. That's a problem. I'm thinking, and I'm overthinking. I was thinking that, let's add A and B, but add c, c should be, you know, very big number. In that case it will kind of, in that case it should, you know, like it should return back and come back one more time. You should sleep. No, I should not sleep. You should sleep. I don't sleep. Mm-hmm. Zero, no, not zero. Zero, no. Increment, no. Add, no. Invert, no. What if we take this inf and give increment? I'm not sleepy. I'm not sleepy, guys. I'm not sleepy. I am not sleepy. I am not sleepy, guys. F plus 1, it is 0. Yes. Look. We should make it simple, guys. Let's give me one more time. Give me one more time. Look. 10 minus 0 0 is equal to 10, right? 1 0 minus 0 0, it means 1 0, right? It means 10 plus 0 0 minus 0 0. 10 plus 0 0 plus 10. What it will be? It will be 4. 10 11 0 1, right? 10 plus 10 10 plus 10 10 plus 10 is equal to 1 0 1 0 0, right? 4 bits. Because we don't have 4 bits, it will be, you know, like 0 1, like 1 0 1 1 0 1. But this is incorrect. Let's go to another example. Let's go to another example. 10 plus 0 1. Not to derive, in order to derive to 0.1, we need to add 10, you know, here. Proof? Okay, let me to prove it. What? Oh no, binary 2, binary of 2. in here it is not in binary, guys, you know. Here this plus is not a binary. It is arithmetic operation, you know. It's not increment. A minus B is equal to what? Something less than A equal to A, B, C, okay? A higher than C and then B. A has a limit, has a limit. A has a limit. Stupid, 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 stupid. We should fix. B can be 0, B can be 1, B can be 10, B can be 11, B can be 0, 1, 1, 1, 1. Type she. Type she. What do you mean? What type she? In 16-bit, the maximum number is what? Maximum number is, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And if we increment one more, you know what it will be? You know what it will be? Guess? Any guess? It's just 0, guys. I will prove you. This is 0. I invert 0 as this one. This is the value, right? And if I increment this guy to 1, look, add 1 to the 16-bit value, it will be 0. So here I add one more increment to here, it will be 1. See? So this is how it works. And now subtraction is basically, it is adding. We can add it, you know. I was thinking like a plus something. So we have limit, you know, like we should know the limit. What about A plus B invert it's increment. I need invert. Invert is this one, right? Okay, 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 okay. If we add a plus b, this is incorrect, right? Because b is very big number, right? Because b is a very big number. When we have 1, 1, it should be 0, right? It means, okay, let's do this simple task local. It is 0, and then inverse this one. No, no, no. What about if we add increment in between? No, no, guys, no, it's wrong. It's wrong. How stupid I am, guys. 1 minus 0, 1 minus 0. It should be here. Maybe increment is before. It is cloudy outside. It is so beautiful. It is cloudy, a little bit foggy. Outside temperature is 30 degree. There is no sunshine, but the sky is cloudy. At somewhere, at another place, it is blue. I think clouds are coming. I think it will rain in afternoon. No, it's wrong. I don't know. I don't know, guys. Help! So difficult. Do we have any hints? They don't have. Okay. How affects inf16 to the numbers? Inf. Okay, if I get inf, if I have inf to the b, it will be this value. What about if I test, like this is 1. I think it is helicopter or it is plane. Seems like plane. Helicopter will be more noisier. Okay, how this bitwise inversion works? So, it knows this guy. This guy knows the limit, and limit minus the value is inversion. Okay, how can we do here, for example, where we are? So here c is equal to what? That says limit. Okay, limit minus a is equal to what? Some kind of value plus limit minus b. Can I say this is equal to c? Let's take it. Let's think. Okay, limit is 111. 111 minus a is at 0.1 plus 1. This is 0, 0, right? Limit will be what? 1, 1. What is the output? Output will be 0.1. Okay, we need one increment here. Plus 1. 10. Okay, one condition passes. Second condition, then 10. 10 is 0.1 plus 0.1. 1 minus 0.1 is 10 plus 1. It will be 0.1. Oh yes. So it means limit plus 1 increment 16. This c is, it's a binary, right? But increment is not binary, right? Increment is 16 degrees. 16. We have a problem here. It says minus 1. Increment, invert, right? Limit minus a plus minus b, then plus 1. This increment is not here deleted. F. Now, why? In this case it is working, but in this case this is limit minus b, right? Limit minus a, but this one is, this one is not one. This is bit, 1 bit, one. Move it to one to the right side, right? No, this is adding. Say 1 minus 1 should be 0, right? It should be 0, but this is not 0. Now it's wrong. No increment here. Oh guys, do you have any problems with stream quality? Look, our formula is correct, right? Limit minus a plus limit minus b plus 1. Limit minus a means this one. Limit minus b is this one. We do a summation. We have this value. No, no. Maybe we should have a break. Maybe. Now look, let's follow strictly, okay? Let's do it strictly. Who is the boss? Limit minus a. This one. Yes. Limit minus b. This guy. Yes. And we do the summation. Yes, done. Plus 1. Plus 1? 1 is here, you know. We are adding 1 bit, okay? 1 bit to it. We add 1 bit. If we add 1 bit means no, I don't need it. One bit. One bit, one bit, one bit, one bit, one bit, one bit, one bit. Are you sure that this formula correct then? Why it's not working? Plus 1 means plus 1 shift, right? Plus 1 shift. Don't increment by 1, increment by 1 shift. One shift, how would it represent 1 shift? Increment isn't it that one? Look, in order to this to be correct, we need how many shifts? 1, D to E1, E to F2, F to 0, 3, 0 to 1, 4. With 4 steps. So here we should add 4. How to add 4? From where to get 4? Is this 4? If I like, is this 4? It's 2. Do you want me to do that? Is it cool? Is it cool? No, it's not cool. It's not cool. We need a 4. We need one more. We need one more. Kind of correct. Satisfying too. Kind of correct, but not all. What if I do like this, guys? Is it cool? No? I should change my position, right? No, you can't see. You should see like this. This is better. This should be correct, but it's not correct. It's false. It's broken. This guy plus this guy. 1 minus 0 is 1, right? No, next help. We need help, guys. We need help. They're saying like a plus a minus b is equal to c. It can be limit and something. A plus in p plus 1. This was difficult one, you know. This was difficult. This was difficult one. But why my formula is incorrect? My formula is that a minus b equal to c, c equal to limit minus a, limit minus b. Look, I have a. If I iterate b times, I cannot go to the b. If I iterate a times, I go to a. If I iterate inverse of b, I can go to b plus 1. Insane. Insane. Good, guys, good. Good. It is, wow, it's 3 hours. Why? Wow. Should output 1 if and only if all bits in the input are 0. If all is 0, right? If all bits in the input are 0. No, it's incorrect. Maybe this is not the best way. Oh, let's read the. Did we do like? Do we have the best way? This is optimal. I see. Let's go. Next level. Less than 0. Output 1 if input is 16-bit number is negative. If it is negative. What is this? We only have this one. Okay. Easy, easy. Why we stuck in that stupid subtraction one? We just did. We just decided that it's quite big, complicated problem. But no, it's not a big problem. It's not big deal. Guys, congratulations. We did arithmetics. Now we are doing switching. Switching. A select component selects one of the two input bit for output. S bit indicate which indicate if 0 D1 selected, if 1 D1 is selected. Let's think. If C is 1, use this one. Use this one. Use this one. If C is 1, use this one. If this is 0, use this one. If C is 1 and this is 1, return this guy. If C is 0, if C is 0, and this one, return this one. This guy or this guy? Let's go. Switch component channel data bit through one of the two output channels. So C selected determine if the data bit is dispatched through C or C0. Okay, we have C and D. If C is 1 and D is 1, go to use this one. If C is 1 and D is 1, go with this one. Right. But if we can again use inversion. But no. Okay, with these 16 bits, it's a bit complicated because there are many numbers, so they are a bit ambiguous. We now have set of different operations available. Yes, the core of a processor is the ability to select different operations based on input. We start with the unit, which select between 4 different bitwise logic operations. Okay, we have now logic unit for 16-bit. Look, if we have 1, okay, we have OR, invert, OR, and what does select? Guys, can you hear me clearly? Is there any problems? I think I have 0 viewers. If someone is listening, just type on chat. Look, if it is invert what? Invert X. Oh my god. Drop rate, drop rate, drop rate. Look, if it is PP1 or OP1 is 0, G0. X and Y. If it is 1, XOR. Same. If this is POP0, X and Y. X and Y, but if OP is 1, 0, 0, 1, 0. Opt 0. We can use NAND, right? when this is on. It's always on. When both are on, it should be invert X. It is 0 invert X. I'm stuck again, guys. Arithmetic logics memory. So, oh my god, arithmetic logic memory processor. Oh my god, oh my god, oh my god. We need to fix it. I think, D1 should go to another selector. When both is 1, invert, right? When no, go to another selector. It should be like this. I'm sure, definitely. In that case, if it is 0, 1 and 0, it should be HOR. It should go like this. Otherwise, another selector. See what's happening. I need NAND for this guy. And if it is 0, it means this way. It means OR. Or this way. Ah? Really? Okay, maybe we did a mistake. When we have a 0, 0, it means and, right? X and Y. When we have 0, 0, it is X and Y. We didn't connect it. We just connected. Excellent. Guys, we are solving problems. Almost done. Guys, congratulations. So now, way more simpler. Now you understood, right? You understood the logic, how to do this. Okay, let's read this one. The 2-bit flag of op 0 op 1 determine which of the following 4 arithmetic operations are performed on the two 16-bit input x and y. We did it, didn't we? We did it. How we did is that we use nan, another nan, and one more nan. Actually, was that our solution effective? Oh, no, it's not effective. We can solve with lower, less. Okay. 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 X minus 1. X minus 1. What? Okay, we have x plus b. That's clear. We have x minus y. That's clear. But we have also x plus 1, x minus 1. No, 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 no. I need to create one, you know. I need the one here. If it is, you know, if it is 1, 1, x minus 1. Otherwise, what? If it is 1, 0, x minus 1, x minus 0. X. Guys, can you hear me? No? Fine, fine. Now we can. Now it's everything fine. Now fine, fine. Seems like the internet was bad. Now it's good. Next step: LU arithmetic logic units. 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Actually, how was the solution? Possible to solve with fewer elements. Okay, fine. ALU combines logic and arithmetic operations. Background is beautiful, right? I think you don't know where is this? Where is this place? Uh, I think nobody knows, except my. No, if I tell some people, then you can figure out. I went exactly to that place this summer at 5 a.m. 4:50 a.m. at that place exactly. It was not exactly like this, but it was giving that vibe, that amazing feeling. Okay, now we need to figure out to fix this LU. If we fix this, guys, then we are good to build a computer. Okay, why we need to build computer? We need a computer, guys. I am hungry. I need to have a breakfast. Maybe should I turn off and start one again or what? I don't know. Two additional flags modify the appearance. 0000 is tab input. Our input is U, OP1, OP0, ZX, CV. And we have two operations. I think this should be it should be more faster. We have arithmetic unit, right? And we have logic unit also. Why I cannot ask for help? Look, I can make it bigger, yes. Mm-hmm. We have a logic unit, we have arithmetic unit. X minus y minus 0 minus x 0 minus x. Okay, this is done by arithmetic unit. This is done by logic unit. OP1, OP1, OP0, OP0, x to x, y to y, OP1 to OP1. I'm hungry, guys. I'm hungry. I don't know. Should I go and cook now? And like, don't not do this stream. I just will fry eggs. I need like maybe 3 eggs. Okay, we have select, right? Done. If it is u is 0, if u is 0, logical. If u is 1, arithmetical. Okay, done. I mean, our most of the task is done. Then we should care about these two guys. We have a flag. If CV is 1, okay. If CV is 1, X and Y inputs are swapped. Swapped means X go to Y, Y go to X, and this guy go to here. Okay. Excellent. What about the next one? Okay, we have one viewer. Okay, congratulations. Next one. 1ZX flag is 1. The left operand is replaced with 0. Swapped. Oh, it is inter. Oh my god. Oh my god, this is tricky. But we will solve it, no problem. We will solve this problem. Look, when they are both are 1 1, we need 3 nans just. Yes, this is important one. I know this way, but it seems like very simple, very stupid way. NAND, it is 1 when it is 0 0. X and Y, right? And right, and Yes, my problem is that I don't speak. I should speak. I should speak. I should express my opinions, express my thinking inside of my brain. Otherwise, the stream will be boring, right? Absolutely, absolutely, absolutely. Let's solve this problem. Last problem, okay? Let's just fix this problem. This is fine. This is fine. But our x should not directly go here, you know? X should go another place. We have arithmetic unit and we have logic unit, right? Yes, you are right. P are fixed. Our x are not. X and y are different. So x and y should not come from here. It should come from somewhere else. From here, for example. But this, no, don't need it. Yes, we need it. Yes, select. Okay, when both are 0, 0, it means nothing affected, right? In that case, x, if it is affected, it's 1. Why you are not connecting? And the same for y. X and y. What? Bullshit. Okay. Okay, when it is 1, 1, our x should be 0. then our y, if it is 1 1, should be what? Should be x. Yes. I don't know this one. Select another one. If the x is 1, left operator is become 0. Left operator is 0. If CV is 1, x and y are swapped. X is 1, it will be y. Otherwise, 1 0. I'm a bit confused, just wait. If both of them 1, in that case, x should be 0, okay? Right. Else, if cx is 1 but this is 0 1 0, x should be what? 0. Another condition. If this is 0 but this is 1, x should be y, right? Otherwise just x. Okay, this is for x. Now for y. Okay, it depends also on this guy. If this is the x is 1 but it is 0, it should be just y. If this is 0 but this is 1, it should be x. Otherwise y. Check solution. No. Why? Why it's no? I cannot see my screen, my own screen. Okay, when we have 7 and 4, off. This 4. Congratulations. Of course, because here we are duplicating. What we are duplicating? We are duplicating because this y stays consistent. So we solved this problem. Next problem. Condition. All these things are solved with this processor stuff. Can you see this processor? This is microprocessor, microboard. The processor inside is very basic, one core processor. It has a Wi-Fi, it has a Bluetooth connection. We can write C code, we can compile, we can run simple things, but they are not that complicated. So okay, the three flags indicate three possible conditions. Let me to have a breakfast first. Breakfast first. I will prepare some fried eggs. Then let's continue. Okay.